Hello. In the previous video, we studied how to find eigenvalues, eigenvectors, and eigenspaces. Today, we discuss about diagonalization for a matrix. And we see when a matrix A can be represented in the form P to negative 1, diagonal, and P. The diagonal matrix in here contains lambda 1, lambda 2, and so on, lambda n as eigenvalues of matrix A, okay, on the main diagonal. All the entries are 0. Actually, we already discussed the following problem. We have matrix A equal to 1, 3, 0, 3, 1, 0, 0, 0, and negative 2, right? And we found all eigenvalues of this. We have 4 and negative 2. That is eigenvalues. And we also found eigenvectors corresponding to these eigenvalues. Let's say for 4, I have 1, 1, 0. But for negative 2, I have 1, negative 1, and 0, 0, and 0, 1. We know that the multiplicity of negative 2 in this case 2, right? And the eigenspace corresponding to negative 2 has dimension equal to 2. At the same time, the multiplicity of 4 is 1, and the eigenspace for this eigenvalue is one-dimensional subspace. But in total, the multiplicities give you 3, because 2 plus 1 is 3, right? That is the dimension of the whole space. If we put P equal to 1, 1, 0, 1, negative 1, 0, 0, 0, 1, then we have P to negative 1, AP is equal to 4, 0, 0, 0, negative 2, 0, 0, 0, negative 2. This is the identity I asked you to do in the previous video. It's pretty easy, just matrix multiplication. But what does it mean? That means, in this case, the matrix P diagonalize the matrix A. You see that? You multiply P to negative 1 from the left of A, and with the P from the right of A, you get a diagonal matrix. And then forget, here's the thing. For the matrix P, if you put the first column is 1, 1, 0, which is eigenvectors of 4, right? So you have to keep 4 in the first position, in the first column. Make sense? So the second column is eigenvectors of negative 2, so you keep negative 2 in the second row, and the same thing for the last column right here. I mean, in case if you have 3 different eigenvalues. Agree? So we say, yeah, P diagonalize the matrix A. And as we discussed last time, these two matrices, the diagonal and the A, are similar. Is it correct? And of course, they represent the same linear transformation in different basics. That is the most important. You know, two similar matrices represent the same linear transformation, but in different basics. In this case, A is called diagonalizable. From this example, we have the following observation. The matrix A is diagonalizable if it has n linearly independent eigenvectors. Look at this. We talk about multiplicity, right, of 4 and negative 2. The multiplicity of negative 2 is 2. That means we have 2 linearly independent vectors in that subspace. At the same time, for 4, we have one basic vector 1, 1, 0 for that eigenspace. Of course, 3 vectors right here are linearly independent. It is easy to check. Okay, so A has 3 linearly independent vectors. At the same time, A is matrix 3 by 3, or A representing matrix of some linear transformation in R3 or in 3-dimensional space. So that's why this matrix is diagonalizable. Okay, so we are talking about matrices, but actually we are also talking about linear transformations. Make sense? A linear transformation is diagonalizable if X matrix is diagonalizable. That's it. Okay, so I will not repeat this again. And from here, it's easy to see that two similar matrices have the same set of eigenvalues. Okay, you know, the set of eigenvalues is sometimes called the spectrum of that matrix. Spectrum of that matrix. And of course, that is the spectrum of the corresponding linear combination too, right? So you see, you know, if a matrix is similar to a diagonal matrix, that means that matrix is diagonalizable. That's it. Okay? And the spectrum is nothing but, you know, the set of all eigenvalues. Let's consider the following example. We have matrix A equal to 1, negative 1 and negative 1, 1 and 3 and 1, negative 3, 1 and negative 1. We need to find the matrix P such that this matrix is diagonal. So, of course, we need to consider, you know, if A is diagonalizable or not. If A is not diagonalizable, it's no way to find P, right? So, the first step is to find all eigenvalues of A, right? Find eigenvalues of A. And we know we have to solve the equation A minus lambda I equal to 0, which is determinant, right? So I just subtract from the entries on the main diagonal by lambda, and I take the determinant. So I have 1 minus lambda in here, negative 1, negative 1, 1, 3 minus lambda, 1, negative 3, 1 and negative 1 minus lambda. And I set it equal to 0. So I want to make more zeros in this matrix and then find the determinant. So I can multiply the third column with negative 1 and add to the second, and the third column with 1 minus lambda and add to the first. I have the following one. Negative 1, 1, negative 1 minus lambda. Okay, so here I have 0. 1 with negative 1 is negative 1 plus 3 minus lambda. That is 2 minus lambda. And here I have negative 1 with this would be 1 plus lambda plus 1 is 2 plus lambda. Make sense? And then I multiply the third row with 1 minus lambda, add to the first, the third column. So I have 0 right here, and 1 with 1 minus lambda plus 1 is 2 minus lambda, and then negative 1 minus lambda times 1 minus lambda, right, and minus 3. So I write here, let me simplify this. So this is lambda square minus 1 minus 3, which is lambda square minus 4, right? I have lambda square minus 4 right here. Okay, and then we just erase this because you have equation equal to 0. right? I don't care about the sign of that. I have 2 minus lambda, 2 minus lambda, lambda square minus 4, and 2 plus lambda equal to 0. 2 minus lambda is common factor on the first row. I can take that out. I have 2 minus lambda. On the first row, I have 1 and 1, right? But in the second row, I have lambda square minus 4. What's that? That is lambda minus 2 times lambda plus 2. So we will have lambda plus 2 as common, right? I also can take that out, okay? But let me write this right here, lambda minus 2, lambda plus 2, and in here I have lambda plus 2 equal to 0. So I have 2 minus lambda, lambda plus 2, okay? And here I have 1, 1, lambda minus 2, and 1 equal to 0. This is equal to 1 minus lambda minus 2, which is 3 minus lambda, right? So I have 2 minus lambda, lambda plus 2, and 3 minus lambda equal to 0. From here, I get lambda equal to 2, lambda equal to -2, or lambda equal to 3. So this matrix has 3 eigenvalues. And of course, we can do the conclusion right away. This matrix is diagonalizable. Why? Eigenvectors with respect to different eigenvalues are linearly independent. So you have 3 linearly independent eigenvectors in this situation. So we figure out that A is diagonalizable. Perfect. Now let's find eigenvectors corresponding to these eigenvalues, because we want to find the matrix P, right? For lambda equal to 2, I have 1 minus 2, -1, -1, 1, 3 minus 2, 1, and -3, 1, -1 minus 2, and I need to solve the homogeneous system, right? This is equal to -1, -1, -1, 0, 1, 1, and 1, 0, -3, 1, -3, and 0. So I might ignore the first equation because that is just scalar multiple of the second one. Now I multiply the second row with 3 and add to the third, right? I get the following one. 1, 1, 1, 0 in here, 0, 4, 0, and 0 right here. And of course, I can divide the second row by 4. I make this just 1, and then multiply the second row by -1, add to the first. So I have the following form: 1, 0, 1, 0, 0, 1, 0, 0. From here, I see, yes, x3 is free variable, right? From the second equation, we see that actually x2 is 0. And from the first one, we have x1 equal to -x3. And the general solution looks like -x3, 0, and x3, or x3, 1, 0, or -1, 0, and 1, right? So you already have the first column of the matrix P. Now let's move to the next eigenvalues, which is -2 and 3, right? Let's say lambda equal to -2. So I have the following matrix: 1 minus -2, -1, -1. Here I have 0, 0, 0. Next, 1, 3 minus -2, and 1, -3, 1, -1 minus -2. Minus -2 is 2. So we have 3, -1, -1, 0, 1, 5, 1, 0, -3, 1, and I think that is 1, right? All right, here's 0. And we see that actually we can ignore the third equation because that is just negative of the first equation, right? And I can multiply the second row by -3, add to the first. So I have the following: 1, 5, and 1, 0, 0. And here I have 0. With 5, with -3 is -15, minus 1 is -16, 1, -3, and here I have -4, right? Now I can divide the first row by -4. I can make this just 4 and 1, okay? So I can rewrite like 1, 5, 1 in here, 0, 0, 4, and 1, 0. And you can divide the whole size by 4 again, right? And make this just 1. And here's 1/4. And then I multiply the second row by -5, add to the first. I get 1, 0, 0, 1, 1/4 right here, and here's 0. And -5 is -5, 4 plus 1 is -1/4. Here is 0. Okay, from here I can see x3 again is 3, right? And x2 equal to -1/4 x3, and x1 equal to 1/4 x3. So I have the following solution: 1/4 x3, -1/4 x3, and x3. Okay, I can take x3 over 4 out, and I have 1, -1, and 4. This is my second column of matrix P. Similarly, we can do for lambda equal to 3. I have to solve the following system: 0, 0, 0. And here I have 1 minus 3, -1, -1, 1, 3 minus 3, 1, -3, 1, -1 minus 3. So this is -2, -1, -1, 0, 1, 0, 1, 0, -3, 1, -4, 0. You can multiply the second row with 2 and add to the first, and multiply second row with 3, add to the third, right? So you might have the following one. I will keep 1, 0, 1 in here, okay? And for the first row, I have 0. I have -1. To add to this, I get 1 in here. And the third row looks like 0, 1, and -1, 0. So you can see, yeah, this and the third are the same, right? So I have, this is just equivalent to 1, 0, 1, 0, 0, 1, -1, and 0. And from here we see the third x3 is 3, x2 equal to x3, and x1 equal to -x3. From here you get the general solution looks like -x3, x3, and x3, right? So that is x3, 1, -1, 1, and 1. That is the third column of your matrix P. Now we have matrix P look like. The third column, I have this in here, so I just copy that. The second column is 1, -1, 4. And the last column, and the first column is what? Where's the first column? -1, 0, and 1, right? -1, 0, and 1. Okay, and how to write the diagonal matrix in this case? The diagonal matrix look like the first is corresponding to the first eigenvalue, that is 2. The second is for the second eigenvalue, that is -2. And the last one is for 3. Alright? So now you see, we already talked about diagonalizable linear transformation, right? And in this situation, these 3 columns will form basics: -1, 0, and 1, 1, -1, and 4, -1, 1, and 1 is the basics. Don't forget that. And in this basics, A is diagonal. So what does it mean? That means if you consider the matrix A and the corresponding linear transformation, let's say this is your A, right? Where's your A? Your A is right here. Okay. And you consider some map T, TA, such that TAX equal to AX. And you want to diagonalize your TA. So your TA in this basics looks like it's just 2x minus 2y and 3z. So basically, if they ask you to find basics for R3 or for vector space such that the matrix of your linear transformation is diagonal, you do almost the same thing. Make sense? And your answer in this situation is this basics. And if they ask you to find a matrix that diagonalizes your original matrix or your original linear transformation, you do almost the same thing, but this is your answer. We have different questions in here, but with the same answer. And we know that not every matrix can be diagonalizable. In order to see if a matrix is diagonalizable or not, you need to check the multiplicity, right, of eigenvalues and the number of linearly independent eigenvectors. All right? Thank you and see you in the next video.